One last bit of review before we start learning about calculus and limits. I want to remind you about logarithms. So hopefully already these are true about you, but if not, by the end of this presentation, hopefully you can explain what a logarithm is. Hopefully you can graph logarithmic functions, and hopefully you can both evaluate logarithms and solve logarithmic equations. So first and foremost, what is a logarithm? Well, it's actually pretty short. Just one word. A logarithm is an exponent, meaning the output of a logarithm is an exponent. Well, I would do log base 2 of 4, but let's do log base 2 of 16. That might be a little more obvious. So if we remember a logarithm is an exponent, you already know the word base or phrase base 2 to a power, and we're talking about the same base. We'll get to this in the next slide. Logarithms are inverses of exponentials. Okay, so 2 to a power, that's an exponential. So when we see log base 2 of 16, we want the exponent to put on the base 2 to get 16. Log base 2 of 16 is 4, because 2 to the power 4 is 16. You've probably been taught to always rearrange to put into exponential notation, and that's a tool, but you need to learn to evaluate logarithms without writing in that numbered form. Okay. As I said, a logarithmic function is the inverse of an exponential function. So what do we mean by inverse? So let's see. Y equals e to the power x has a bunch of ordered pairs. 1e, 2e squared, 3e cubed, 0, 1, negative 1, 1 over e. The inverse of e to the x has all these ordered pairs, but with x and y reversed. There's some graph that has the ordered pair e1, e squared 2, e cubed 3, 1, 0. 1 over e, negative 1. That function, I'm sure some of you remember, is natural log of x. And so another way to say that, or something else that's true about inverse functions, especially one-to-one functions, like e to the x and natural logs, is they undo each other. What do I mean by undo? Well, if you did y is equal to e to the power natural log of x, you would get x. E to the power and natural log are inverse operations, just like adding 3 and subtracting 3 are inverse operations. By the same token, y is equal to natural log of e to the x also gives us y equals x. So if we have to sketch, you're probably more used to things like 2 to the power x. That's pretty easy to make a table of values. So 0, 1, 1, 2. 2 to the power 2 is 4. 2 to the power 3 is 8. 2 to the power negative 1 is 1 over 2, or 2 to the negative first power. 2 to the power negative 2 is 1/4, 1 over 2 squared. Okay. So let's sketch that. Let me get some white. And we'll just approximate here. So if that's 0, 1, 1, 2, 2, 4, 3, 8. And then let's think about what happens to the left of negative 2. If we did negative 10, 2 to the power negative 10 is 1 over 2 to the power 10. We get a very small number, but that number is going to be greater than 0. Let's label this f of x equal to 2 to the power x. Uh-oh, I wrote that in the wrong place. We're also going to sketch the inverse of f. And let's make a different color table of values. So because, do you remember this notation? This, what looks like an exponent -1 isn't. We read this as the inverse of f. So making a table of values is pretty easy. Since we know logarithmic functions are inverses of exponential functions. Or, maybe we shouldn't talk about logarithms, an inverse function shares all the same ordered pairs x, y, but just with those x's and y's reversed. So 0, 1 in 2 to the power x becomes 1, 0 in the inverse of f. 1, 2 becomes 2, 1 in the inverse of f. And I'm sure you can copy these. Okay. And so 1, 0 goes about here, 2, 1 goes about there, 4, 2 goes about there, 3, 8 goes over here. Try to make that curve a little smoother. Okay. And this is f inverse of x. And if you didn't already know, this is log with a base of 2 of x. So let's go through and remind, because one of our jobs is to make sure you can evaluate logarithms. What's log base 1 of x? What exponent do you, what is log base 2 of 1? Log base 2 of 1 is 0, because the exponent you put on 2 to get 1 is 0. What's log base 2 of 2? Well, that's 1. What exponent do you put on the base 2 to get 2? 1. What's log base 2 of 4? Well, what exponent do you put on 2 to get 4? 2. What's log base 2 of 8? What exponent do you put on the base 2 to get 8? 3. Okay, this does seem to match up. So maybe that's a good plan. If you're a little bit stuck on graphing a logarithm, think about its inverse exponential function and figure out those ordered pairs. Although I really think you should be able to graph logarithmic functions by now. So I want you to be able to evaluate logarithms. I have a bunch of these ready to go. Write them down. Don't write them down. That's your call. Well, you should probably write some of these down. If you're able to evaluate these quickly, in a way you'll understand this in the future, you should be able to tell us what log base 10 of 10 evaluates to and why. Are you ready? Log base 10 of 10 is 1 because the exponent you put on the base 10 to get this 10 is 1. What's log base 10 of 1,000? Well, we're asking the question, what exponent do you put on 10 to get 1,000? And that's 3. 10 to the third power, 10 times 10 times 10 is 1,000. What's log base 5 of 25? What exponent do you put on the base 5 to get 25? 2. Let's speed things up. You can, of course, pause the video if you need to. Log base 5 of 125 is 3, because 5 to the power 3 is 125. The exponent you put on 5 to get 125 is 3. Ooh, log base 5 of 1. Log base 5 of 1 is 0. The exponent you put on 5 to get 1 is 0. Log base 3 of 81 is 4. 3 to the 4th power is 81. Log base 4 of 16. Are you ready? Log base 4 of 16 is 2. The exponent you put on 4 to get 16 is 2. This next one's tricky. Well, am I messing with you? Kind of, but not really. What's log base 8 of 16? What exponent do you put on 8 to get 16? Well, 8 to the 1st power is 8. 8 to the 2nd power is 64. So something between 1 and 2. Now it's not the exponent 1/2 because 8 to the power 1/2. Oh, shoot, that's in the wrong spot, but this is a hint. 8 to the power 1/2 is the square root of 8. So what are we thinking? What number do you see in common in terms of bases when we say 8 and 16? Hopefully that's a 2. So maybe we can think of it that way. 8 to some power simplifies to be 2. And that's the 1/3 power. Because a 1/3 power, remember, is a cube root. Okay? Except we didn't want to get 2, we wanted to get 16. So let's remind you of another fact. 2 to the 4th power is 16. So this must be log base 8 of 16 is 4/3. We have to take the cube root of 8, we need the exponent 1/3, and we need to raise to the 4th power. Ideally, you could do that in your head, but kind of hard to follow a video of what I am just saying without writing. All right, I'm going to give you a moment to figure out log base 16 of 8. It's a very similar thought process. So we know 16 to the 1st power is 16. 16 to the 0 power is 1. Hopefully you see the common base of 2 between 16 and 8. So we need to turn 16 into a 2 by taking the 4th root. So that's going to be a 4 in the denominator of our exponent. And to get from 2 to 8, we cube. Do you need to see that in the exponential form? Let's try that. So I'm going to start with 16, and when I'm done, I'm going to get 8. So maybe we can work from both sides. 2 cubed is 8, so I need to turn 16 into a 2. How do I turn 16 into a 2? I take the 4th root of 16. Okay, so I guess we need to squeeze something in right here. Or maybe we can just rewrite this as 16 becomes 2 to the 4th. Oh, that's what I should write it as. 16 cubed, that's 2 to the 4th cubed. When you take the 4th root of 2 to the 4th power, we get 2. I'm missing, these don't all match, do they? I need a 4th root here, and so I guess I can think of that as 16 to the power 3/4. All right, so if we're going to solve and show all work, most of us can just, most of us can just write x is equal to 2 because we know 5 squared is equal to 25. But if I have to show all work, I need to, well, this is preparing you for Calculus AB. You can't just, hey, I have the answer. You need to show where it comes from. So how do we get rid of a base 5? Or how do we do that x stuff? Well, maybe I should go back a little. I'm realizing I don't have a blank page. So let's get rid of this. So we need some properties of logarithms here. And basically all logarithms have the same property. Logarithms are a short way of doing exponents. What I mean by that is, way back in first grade, you learned how to add, and you probably didn't do 2 plus 2 plus 2, but you could have done a pair of them, 2 plus 2. And then, probably about third grade, oh, we should probably use x's if we're pretending third grade, you learned multiplication, and multiplication was a quick way of adding a number a bunch of times. And then you got to, I don't know, 6th or 7th grade, and maybe you had 3 times 3 times 3 times 3 times 3, and you were taught about exponents, which is a quick way of multiplying, or at least symbols that mean multiplying a bunch of times. Well, logarithms are a way to manipulate things, a bunch of things that have the same exponent, because a logarithm, what's the best way to say this? On a normal number line, 0, let's just do 1. 1, and then 10 would be here, and then 100 is way over here. Okay, this is a normal number line. When we talk about logarithms, logarithms shrink the distance between the powers of numbers to be the same. And so what I mean by that is, on a logarithmic scale, the distance from 1 to 10, the distance from 10 to 100 are the exact same, because that's an extra power of 10. Okay, that's sort of weird. So on a logarithmic scale, let's put some even spacings on here. If we had a 1 and then a 10, this would be 100, 1,000, 10,000, and then over here, 1/10. The distance between powers of 10 or powers of any number are always going to be the same on a logarithmic scale. So let's think of log base 2 of 2. We know log base 2 of 2 is 1. The exponent you put on the base 2 to get 2 is 1. Log base 2 of another 2 is also 1. Log base 2 of another 2 is also 1. Of course, 1 plus 1 is 3. Now, I'm just going to, this cycle, I don't know, maybe not proves, but might help you remember the properties of logarithms. If you have 3 of something added together, that's the same thing as 3 multiplied by that something. So 3 log base 2 of 2's added together is 3 times log base 2 of 2. Now don't forget, this 3 down here came out of a logarithm, so that is an exponent. So let's think about this. Log base 2 of something has to be equal to 3. And what is that number? 8. So log base 2, let's rewrite 2 as 2 cubed, is 8. And this hopefully helps you remember that, I don't know, the most useful logarithmic property is the number that's on the, the exponent on the number inside of the logarithm can be moved to be a coefficient in front of the logarithm. Okay. But there is something else. There is another rule. Let's see if we can illustrate that over here. And that is when you have logarithms added together, like up here. Logarithms added together, well, when you're adding exponents, that means you're multiplying bases. Let me say that again. When you're adding exponents, that means you're multiplying bases. So log base 2 of 2 plus log base 2 of 2 plus log base 2 of 2 is the same as log base 2 of 2 times 2 times 2, which we already saw way back here, 2 cubed. Let's do a slightly different example of that using these same numbers. Let's see if we can do something similar. Maybe we do log base 2 of 2 plus log base 2 of 4. That's going to be 1 plus 2. We get that same 3, so we know that's log base 2 of something gives us 3. That's got to be 8. So maybe thinking back here, if we're adding exponents, we multiply the numbers. And you kind of already know that rule. If I gave you x cubed times x to the 5th, you'd write x to the 8th power. You add exponents. Remember, these logs are exponents when you're multiplying. Anyways, so you kind of need that information. So if we're going to solve 5 to the power x equals 25, that means we need to get x is equal to, heck, we need to get x equals 2, but we need to fill in the blanks. How do we get rid of that 5 so we can do some math? Well, it's algebra. We need to get rid of 5 to a power. The inverse operation of 5 to a power is log base 5. So we'll apply log base 5 to both sides of our equation. Log base 5 of 25, that's really easy. That's 2. What exponent do we put on 5 to get 25? That's 2. Now over on the left-hand side, we just can't cancel everything out. We'd have an x floating up nowhere. So we need to move that x to be the coefficient in front of log base 5 of 5. And then log base 5 of 5 is 1, so we get the x equals 2. We know we were supposed to get. If you can't show all that work, hey, we have some practice to do. It's not good enough to just get the answer anymore. All right. So what about here? Log base 3 of x minus 2 equals 4. You could probably work that out logically, but it might be quicker to do the work. So we know we need to get x equals. What's the inverse operation of log base 3? That's 3 to a power. So we exponentiate, that's the verb, both sides as powers of 3. We rewrite our equation. Each side has a base, and what used to be on the left-hand side of the equation is the exponent on the left-hand side. What used to be on the right-hand side of the equation is the exponent on the right-hand side. We're allowed to do whatever we want, as long as we do it to both sides of an equation. So let's see, 3 to the power log base 3 of x minus 2. We get x minus 2. And 3 to the power 4 is 81. X is equal to, add 2, 83. Oh, so if these words weren't here, I'm hoping you would already know this is either a calculator problem or something where you're not going to get a super clean number like 83. And the reason I know that, and the future version of you would know we need a calculator, is this base 2 and this base 5. 2 and 5 share no common factors. Now, if we had 2 and 8 as bases, then we have a chance of getting something. Or 2 and 4, something like that. But because 2 and 5 don't really share anything, well, we're just going to have something ready to put into a calculator, but not anything that, I don't know, you guys feel like is a nice number. So we can use any logarithm we want. I'm going to use natural log. It's my favorite log. It will be your favorite logarithm too once we do some more calculus. So I apply natural log to both sides of our equation. Oh, forgot my 5. What am I going to do next? I move those exponents out front of my logarithms. Well, natural log of 2. How about natural log of 5? Well, what do I do next? How do I get these two x's together? Well, I think I'm going to have to distribute and then factor. So x natural log of 2 plus 1 times natural log of 2 is just the natural log of 2 is equal to natural log of 5 minus 2x natural log of 5. Move the x's to the left-hand side. X natural log of 2 plus 2x natural log of 5 is equal to natural log of 5 minus natural log of 2. Factor out the x. What are we left with? Natural log of 2 plus 2 natural log 5, which we'll rewrite into a better looking form. And over here, when you're subtracting exponents, we can divide. So we're going to rewrite the combination of natural log of 5 minus natural log of 2 as natural log of 5 halves. So we're going to do something similar on the left-hand side. First, I'm going to rewrite this. We can take this exponent, or this 2, make it an exponent. So that's going to be the natural log of 5 squared, or the natural log of 25. So when we divide both sides, we'll get natural log of 5 halves over natural log of, can you combine natural log of 2 and natural log of 25? What do you do when you're adding exponents? You multiply. And that would be ready to put into a calculator. Hopefully that's enough to help you out. Let me know if you have any questions.